So here what you can appreciate over here, this is the L mold as you can appreciate. So one arm over here, it is longer compared to this arm. Okay. So how we are shaping or how we are giving a shape. So as you can appreciate over here, see in this way a mold is created, you know, a rectangular shape can be given like this. So depending on that, we can adjust and give a particular size for a particular tissue. So for example, as you can see over here, the two L mold, they are adjusted with each other. For example, for this size, okay, so this is the size that we are using. So already this is the infiltrated tissue. Now this infiltrated tissue is given and we have poured over here molten paraffin wax. Molten paraffin wax has been poured over here in this particular space. And what we have done, that we have taken this infiltrated tissue and we have basically pushed the tissue to the depth or to the floor of this particular mold, such that the area to be cut is in front or is completely on the surface of the block. Okay, so this is basically kept and it is pushed down. Okay, this is how we are basically embedding the tissue. This is called as tissue embedding. Okay, this is a long tissue. Okay, so they are kept longitudinally. If you see, this is the skin. Okay, they are kept vertically, and you see this is the epithelial layer, this is the epidermis, this is the dermis. So when the tissue is cut, all the layers will come. Then again, this is the fallopian tube. This is a round transverse section. You can see the lumen. Okay, you are basically keeping it in a transverse section so that the lumen can be visualized. Again, over here, you can appreciate this is the L mold over here. Okay, this is the tissue that has been embedded over here. This is the tissue over here, and again, the labeling has been done. Okay, now small bits of tissue, as I told you, they are placed in the center as we can appreciate. This is how it is done with the L mold, and this is how it is done with the stainless steel. Okay, and then on top you can give a peripheral plastic ring as well.
Myself, Dr. Jibran Ahmed, presents to you Simply Pathology, and today we are back with a very important lecture. Today we are going to read about the tissue processing part 1. Okay, so basically in today's lecture we will read about the steps of dehydration, then the process of clearing, and in the end we will understand about infiltration and tissue embedding. So let us just revise. So basically, what are the steps of tissue processing, starting from receiving the tissue sample up till we are getting a H&E stain. So the first step is that of fixation that we have already read in the previous lecture, followed by dehydration. Then there is clearing, followed by tissue infiltration and embedding by paraffin wax, sectioning by microtome, and staining, H&E staining. Okay. So in today's lecture, we are going to read in details about these 3 steps, that is dehydration, clearing and embedding, okay, which is also called as tissue processing. So tissue samples requiring processing need to be placed in a fixative as soon as possible after excision from the patient. This first step is essential to prevent autolysis, which could destroy the diagnostic elements, and to prepare the tissue for the rigors of the reagents used in subsequent processing steps. To ensure accurate specimen tracking and maintain patient confidentiality, all tissue received in laboratory must be given a unique identifier. Typically, an alphanumeric code is assigned to each sample. This code follows the specimen on its journey from the moment it is received in the lab to the final pathology report. So we have already read in details about fixation of the tissues in the previous lecture. Okay, so we are just revising. So what are the basic outline of the steps of the tissue processing? Let us see. So this is just the basic outline. So we have already read about the fixation, which is preventing autolysis and which stabilizes the tissue to maintain the cellular structure. So we have read about this in detail. The next step after fixation is dehydration. So it is going to remove water and any unbound fixative from the tissue. That is followed by clearing. So whatever dehydrating agent you have used, you have to remove the dehydrating agent as well. So it is going to displace the dehydrating solution, making the tissue components receptive to the infiltrating medium, that is the paraffin wax. Okay, and the next step after clearing is infiltration, wherein we are going to permeate or infiltrate the tissue with a supporting medium, that is paraffin wax. Why this infiltration is required? Because if you cut a tissue section just like that, it is not going to give you a good section. Why? Because it is going to fold on itself. But if you infiltrate with wax, okay, if you infiltrate the tissue with wax, then taking sections become easier. So for that purpose, we have to infiltrate the tissue with wax so as to make it suitable for microtomy or for tissue cutting. Okay. Finally, whatever substance we are infiltrating inside, we also have to support the entire tissue in a mold. Okay, that is achieved by embedding. So over here, there is an orientation of the tissue sample in a support medium to create a tissue block which is suitable for sectioning. Okay. So over here, this is the tissue that we are taking, the piece of tissue. The process of fixation is done on that. After that, we have to remove the excess fixative and we have to remove the water out of the tissue, the free water by dehydration. That is followed by clearing of the dehydrating agent over here. So we are using a clearing agent, mainly xylene. That is followed by infiltration with some suitable support medium. Okay, around 58 to 60 degree, we are using paraffin. And then that particular tissue needs to be embedded in a particular tissue block. Okay, that is suitable for cutting, for microtomy. Okay, then we embed it in the support medium. That is again the molten wax, that is the paraffin we are using over here. Okay, infiltration and tissue embedding. So these are the major steps of tissue processing. Okay, in short. Now we will have a detailed discussion, okay, of each of these steps. So the next step after the fixation is processing of the tissue. It is an important step because proper or poor processing of the tissue may significantly affect the section, cutting and staining. So what is the aim of tissue processing? To provide sufficient rigidity to the tissue so that it can be cut into thin section for microscopic examination. So what is the principle in tissue processing? The water within the tissue is removed. How? By the process of dehydration. And another medium, usually it is paraffin wax, is infiltrated and impregnated that provides adequate support to the tissue that is going to allow microtomy or tissue cutting. Okay, thin sections can be taken for microscopic examination. So the main essential steps include dehydration, which in this step the water is removed from the tissue. Now remember water, why it is required to remove the water? Because water does not mix with wax, because ultimately we have to infiltrate the tissue with wax. So we have to remove the water because water doesn't mix with the wax, and therefore to infiltrate the tissue with the wax it is necessary to remove this water. Okay, that is why dehydration is required. Okay, the next step after dehydration is clearing. Now why is it required? Now we have removed the water, but instead of water the dehydrating agent has also come into place. Again we have to remove this dehydrating agent also. Okay, because not all dehydrating agents are mixing with the paraffin wax or the molten wax. Okay, so therefore we have to clear or we have to remove the dehydrating agent as well. So this is needed to clear the dehydrating agent and to facilitate the transition of dehydration and infiltration or impregnation. The clearing substance, okay, whatever we are using for clearing, especially we are using xylene, it is usually mixing or it is miscible in both dehydrating agent as well as in the infiltrating or impregnating medium. Okay, remember this point. After the clearing, after we have cleared the dehydrating agent, we are having infiltration and impregnation. So in this stage, the tissue is infiltrated with a supporting medium, usually paraffin wax. Okay, and then also they are embedded in a suitable tissue block, and this is done to provide adequate rigidity to the tissue to carry out microtomy or to take thin sections for microscopic examination. Okay, so now we are going to see what are the factors which are influencing the tissue processing. So when the tissue is immersed in a fluid, an interchange occurs between the tissue's internal fluid and the surrounding solution. Now the surrounding solution will be different grades of alcohol. It will be xylene, it will be paraffin wax. So there are different stages over here. Okay, so let us see what are the factors which are affecting the tissue processing. The first factor is the size of the tissue sample. The optimum size of the tissue is very important for effective processing of the tissue. The smaller the size of the tissue, better is the infiltration of the embedding medium. Optimum thickness of the tissue should be kept as 3 to 4 millimeter only, number one. Number two is agitation. Now the tissue gets better contact, okay, with the surrounding medium if it is completely immersed and gently agitated. So what is happening? You should completely immerse the tissue, for example, in alcohol. Now what is the use? That if you completely immerse, then it is completely coming in contact with the nearby agent. Now if you agitate, okay, the agitation will continuously cause removal of the fluid from the surface of the particular tissue, and that particular fluid is replaced by fresh fluid. Okay, so the agitation causes continuous removal of the fluid from the surface of the tissue, okay, and its replacement by fresh fluid. This has better effect of action of fluid on the tissue. Most of the commercial tissue processors, they have the facility for agitation. It is important to note that too rapid agitation may also cause damage to soft and delicate tissue. Now the mechanism for agitation in automatic processor is either vertical agitation or it can be rotatory agitation. Okay, or they can be pressurized removal and replacement of fluid at timed intervals. The next important factor is heat. Now, heat increases the rate of penetration of the fluid within the tissue, whereas low temperature impedes this whole process. Impedes means this slows down the process of tissue processing. The present commercial tissue processors have the facility to heat the tissue in all stages of processing. Excessive exposure to heat can cause shrinkage and hardening of the tissue, which negatively affects subsequent staining and immunohistochemistry. Then comes the viscosity. The viscosity of the embedding media also affects the processing. Higher viscosity of the medium lowers the penetration rate into the tissue of that particular embedding media. Heat reduces the viscosity of the medium and helps in better penetration. The next important factor is vacuum. Okay, application of negative pressure facilitates tissue processing. Vacuum will help to remove the entrapped air from the tissue and thereby enhances the penetration of the fluid within the tissue. Negative pressure will also increase the volatility of the clearing agent and therefore it will help to remove the fluid from the tissue. Vacuum aids in removal of air pockets in case of porous tissue, for example, the lung. And lastly, processing the solvent contamination. Now remember, other factors are, now for example, you have one reagent. Now, how many number of blocks have been processed with that particular fluid or with that particular reagent? Okay, so the number of blocks on each run or the tissue type, okay, which kind of tissue you are using. Some tissues are requiring a lot of dehydrating agent or they require exposure for a long period of time. Even the size of the tissue, even the frequency of the run, how many times you are doing the runs, okay. Using sponges and cross contamination of processor solvents will influence how often the solutions should be rotated between the stations or changed to maintain processing quality. So this is also again another factor which is basically affecting the tissue processing. So what are all the factors? So one is the size of the tissue sample, agitation, heat, viscosity, vacuum, and processing the solvent contamination. Now we will discuss about the first step of tissue processing, that is dehydration in details. So let us read about that. So basically every tissue contains some amount of free or unbound water molecule. As the commonly used supporting medium, paraffin, is not mixing with water, so it is necessary to remove the free water molecule from the tissue for successful infiltration and impregnation of the supporting medium, that is paraffin wax. Now dehydration displaces the residual fixative as well as the cellular water. Now remember one thing, that water inside the tissue, they are available in two forms. One is the free and one is the bound form. Now remember, the bound water molecule, it is an integral part of the macromolecule of the cell. That is, it is the integral part of the nucleic acids, proteins, carbohydrate inside the cell. Correct dehydration schedules during tissue processing should only remove the free water, leaving behind the bound water intact. So your dehydrating process should be such that only the free water is removed, whereas the bound water inside the protein molecule or inside the nucleic acid, they should remain. Now graded alcohol for appropriate duration are used in dehydration to remove free water and keep the bound water in place. That is why we are using graded alcohol, that is for example 70, 80, 90% like that, and that too for an appropriate duration only, because our aim is to remove only the free water and not the bound water. Also, one another very important importance of using graded alcohol is that the sharp difference of the concentration gradient between the tissues and the dehydrating fluid may cause sudden rush of fluid or water out of the tissue, and this may cause damage to the delicate tissue. Therefore, dehydration should be done gradually from a low to the high concentration of dehydrating fluid. For example, you start from 70% concentration and you go towards 90 or 100% like this. Okay. Now, when the tissues are exposed to heat or when they are kept for excessive time in higher grade alcohol, that is in 95 or in 100% alcohol, they are kept for a long duration of time. As I told you over here, if they are kept for a longer duration of time, then what happens that along with the free water, the bound water is also removed. And what happens when bound water is removed? Whenever the bound water is removed, it is going to produce over processing artifacts such as shrinkage, parched earth effect, abnormal staining, as well as dry brittle tissue during microtomy. For this reason, the specimens are best processed through graded alcohols of increasing concentration for an
appropriate period of time. So there are two things you should keep in mind. Okay, gradation is important. Why? Because we do not want a very sharp difference between the concentration gradient between the tissue and the dehydrating fluid, because we do not want to damage the delicate tissue by sudden rush of water out of the tissue. Number one. Number two, we do not want to keep the tissue for a very long period of time in dehydrating agent, because that is going to remove the bound water also, which is going to cause over-processing artifacts and make the tissue dry and brittle during microtomy. Remember these points, they are asked in the exam. So very importantly, this is about when we are increasing the duration of dehydration. What about if we reduce the duration, or if dehydration time is not adequate? So too little time in dehydration fluid may be insufficient for removal of free water molecule. Incomplete dehydration will impair the penetration of the clearing agent into the tissue, leaving the specimen soft and non-receptive to paraffin wax infiltration. Now thin 2 to 3 millimeter tissue needs less time in dehydration fluid than the thick 5 millimeter tissue. Okay, than the thick 5 millimeter tissue. Now if you look at the individual dehydrating agent, we are going to see the first and the most commonly that is used is ethanol. So ethanol or ethyl alcohol, it is the most popular and most commonly used dehydrating agent. Ethyl alcohol is flammable liquid. It is relatively rapid and efficient dehydrating agent. However, licensing is required for using ethanol, okay, and from the government you should take the license, okay, for laboratory use. Now, as a dehydrating agent, ethyl alcohol is used in 50%, 70%, 90%, 100% concentration. So it is an increasing gradient. Why is there this gradation? You know, we have discussed that. For delicate tissue, the dehydration may be started at even a lower concentration of 30%. In routine laboratories, 70, 90, 100% alcohol for 2 hours each is sufficient for dehydration of the tissue. If tissue is immersed in ethyl alcohol for a long time, we know that bound water will also be removed and it can make the tissue very hard, dry and brittle. Now, to this ethanol, remember, when we are placing the tissue during the tissue processing, we are also adding anhydrous cupric sulfate in the final container. So what is the use of this? The anhydrous copper sulfate, it is a white powder that draws the water from the alcohol and thereby helps in dehydration. So for example, if this is the particular vessel and you have added lots of tissue cassettes. So over here at the bottom we are adding anhydrous copper sulfate. Now what happens that the dehydrating agent, that is the alcohol, is here. Now that is going to remove the water from the tissue. So ultimately the dehydrating agent, that is the ethanol, will become saturated with water. So this anhydrous copper sulfate over here, it is going to help to absorb that particular water, and that is going to prolong the longevity of the ethanol, because they will be able to absorb more amount of water. So approximately 1 centimeter of this powder, that is anhydrous cupric sulfate, is kept in the bottom of the container. The cupric sulfate powder should be covered with 2 to 3 layers of filter paper to prevent any coloring of the tissue. Now very importantly, when the copper sulfate will become hydrated, now for example this copper sulfate at the bottom, it has completely absorbed water and it is completely hydrated, then what will happen? The color of the powder, this white powder, will become blue. This will give us the warning signal to change the alcohol as well as the copper sulfate powder. So what is the use of this copper sulfate powder? Because it is removing the water from the ethanol, it is increasing the lifespan and the activity of the ethanol, number one. It is helping in better dehydration, and it is also acting as a good indicator to change the alcohol once it is turning into blue. Okay. Now, what are the other dehydrating agents? We are having methylated spirit, also known as denatured alcohol. It contains 99% ethanol and 1% methanol. Then we have methanol, which is clear, colorless, volatile, inflammable liquid. It can be used as a substitute of ethanol, but it is rarely used because it is very highly volatile and it is having a high cost. Then we have butyl alcohol, again used as a dehydrating agent both in animal and plant histology processing. It is a slowly acting dehydrating agent and takes longer time than ethanol. However, remember the tissue shrinkage is less with butyl alcohol. Isopropyl alcohol, if you see, it is available as isopropanol. It is again miscible with water as well as liquid paraffin. So it is very suitable. It is a relatively rapid acting non-toxic dehydrating agent causing minimal tissue shrinkage, and it is also a good lipid dissolving agent. Okay. Then apart from these, there are other dehydrating agents other than alcohol. So they can ask you to name some dehydrating agents other than alcohol. So what are those? They are dioxin. Again, it is miscible. It is mixing with both water and molten paraffin wax. As I told you that not all dehydrating agents are insoluble in the infiltrating agent. So some of them are miscible, but not all. That is why we are using clearing agent.
Now, this is a rapidly acting dehydrating agent and produces very little shrinkage. Tissue can be kept in dioxin without any harm. The dioxin liberates highly toxic gas and proper ventilation is mandatory for its use. Again, it is expensive. Ethylene glycol, it is colorless, odorless fluid. Cellulose is a rapidly acting dehydrating and tissue can be kept in it for longer duration. Then we have acetone. Now, acetone they call it as a poor man's dehydrating agent. Okay, it is colorless and inflammable liquid with a very pungent ketonic smell. It is miscible with both water and alcohol. It produces tissue shrinkage and prolonged use may cause brittleness of the tissue. It is best used in fatty tissue processing. So now here we will compare the different dehydrating agents. So ethyl alcohol is rapid, efficient, but the basic disadvantages need license, inflammable, and prolonged keeping in this ethyl alcohol may make the tissue hard and brittle. Methanol again is good, but it is highly costly and volatile. Isopropyl alcohol is very good, okay, but very importantly thing is all the things are there over here, but it is I think expensive and also not possible to use in celloidal technique. Dioxin again, it is as good as isopropyl alcohol, rapid action, no shrinkage of the tissue, it is also miscible in both the water and as well as the tissue paraffin wax, but again it is creating highly toxic gas and you should have a proper ventilation. Ethylene glycol again is rapid, again no graded solution is required and tissue can be kept in long period of time, but the thing is it is very expensive and clearing agent is needed. Acetone again has a rapid action, cheaper than ethanol, good for fatty tissue processing. The downside of acetone is it evaporates quickly, it is inflammable and prolonged use may cause shrinkage and brittleness of the tissue. Okay. The next important step that is there, that is called as the process of clearing. So after the removal of free water molecule from the tissue, the next step of tissue processing is to remove the dehydrating agent itself from the tissue. Why? Because many dehydrating agents, they are not soluble in the infiltrating or embedding or impregnating material. Most commonly we are using paraffin wax. The clearing agent should be miscible or they should dissolve in both dehydrating agent as well as the embedding medium. The refractive index of the clearing agent is similar to the tissue and therefore it gives a clear appearance of an anhydrous tissue. So the completely transparent tissue indicates the end point or the terminal point of the clearing process. Any opacity of the tissue signifies incomplete dehydration. A good clearant will also dissolve the lipids which can slow down wax penetration. Now the clearing agent with low melting point is easily and quickly removed by molten wax, whereas the clearing agent with a high melting point takes time to be removed by embedding medium. The clearing agent with a high viscosity has a low penetration rate, and if you heat it, the viscosity will become less and therefore the penetration rate will become high. Prolonged exposure of the tissue in the clearing agent can also make the tissue brittle and more friable, therefore optimum time for clearing is necessary. The amount of clearing agent should be 40 times the volume of the tissue for clearing. So let us just summarize everything. So what is the aim of the clearing agent? It is to remove the dehydrating agent, that is the alcohol, to facilitate the infiltration by paraffin wax. Now it is to make the tissue clear and to improve the tissue for microscopic examination. The ideal clearing agent should have a low viscosity, so conversely the penetration rate is high. Low melting point is there, miscible with both alcohol and molten wax, no tissue damage, less toxic, less inflammable and should be cheap and easily available. Now, the volume of the clearing agent required is 40 times the volume of the specimen. Smaller biopsy is kept for 1 hour, whereas larger tissue, there should be 3 changes in xylene for 60 minutes each. Okay, so there should be 3 xylene and 1 hour, 1 hour, 1 hour in each xylene. Okay, for larger tissue. End point is when the tissue becomes completely transparent. Now, prolonged exposure to the clearing agent can again make the tissue brittle and more friable. Now there are different kinds of clearing agents, like we are having xylene, toluene, chloroform, amyl nitrate, cedar wood oil and limonene. Let us see the individual agents. So xylene, if you see, it is the most commonly used clearing agent in the laboratory. This is clear and inflammable liquid. The small pieces of tissue are cleared rapidly by xylene within 30 to 60 minutes. It is an excellent lipid solvent but has the negative characteristic of drying the tissue specimen. Prolonged exposure to xylene might make the tissue hard and brittle. So this is a downside. And another downside of xylene is that it can cause drying of the tissue and induce some artifacts. Toluene has almost similar properties of xylene. However, it does not make the tissue hard even after prolonged exposure, and the action is slightly slower than xylene. It is flammable and toxic. Chloroform, if you see, it is highly volatile, non-inflammable, expensive. It is quite expensive and it's a toxic carcinogenic agent. So you should have basically a closed system, okay, for using chloroform, not in the open system. Now, the penetrating power of chloroform is lower than xylene. However, it does not cause any hardening of the tissue or tissue shrinkage, and it is mainly used for dense tissues like uterus muscle. Presently, chloroform is rarely used in laboratory. So, what are the other clearing agents? We are having esters, okay. So, these are less toxic and may be used in manual processing. They do not cause tissue hardening even under prolonged exposure. Then we have cedar wood oil, which is an expensive rapid clearing agent mainly used in clearing the dense tissue. Limonene, if you see, it is a clear liquid. It does not cause any tissue hardening. However, removal of limonene from the tissue by paraffin wax is difficult. So let us compare the different agents. So as we see, the tissue shrinkage, hardening, they are very common with xylene. Okay, it is irritant but less harmful and it is cheap. So it is most commonly and widely used clearing agent. Toluene have everything same, but the tissue hardening is not there. It is basically everything is same like xylene. Chloroform, again, minimum tissue shrinkage, hardening, and it is not even inflammable, but it is generating dangerous toxic gas and inhibitor in heating. So you should have a closed system. Of proper ventilation has to be there. Another downside is very expensive and it is toxic and carcinogenic agent. Esters, again they do not cause any tissue shrinkage or hardening, and it is having a very high cost. It has a very high cost. Okay. Next, we are going to read about infiltration and tissue embedding.
So next we are going to read about infiltration and embedding. So basically the next step after clearing is infiltration and embedding. Now the clearing agent within the tissue is removed by the process of diffusion. The tissue space is now infiltrated with the embedding media, most commonly paraffin wax. Usually the molten wax is used as an embedding media. After cooling in the room temperature, the molten wax is solidified to provide support for cutting into thin section. I will explain you in detail that how this process is carried out, so do not worry. Now, why this infiltration is required? Okay, so infiltration must be sufficient to displace the clearant, that is xylene, from the tissues. Otherwise, the wax will not harden properly and it interferes with microtomy as well. So, tissues which are not allowed to infiltrate for long enough will be soft and crumbly, making sectioning difficult. Now, this is when there is insufficient, embedding or infiltration. Now, on the other hand, too much time in high temperature wax can also cause excessive shrinkage and produce dry, brittle tissues which are equally difficult to section. Once infiltration is complete, the tissues are embedded into the paraffin wax block to enable the sectioning on the microtome. Okay, so after infiltration, we are carrying out tissue embedding into paraffin wax block. So what are the qualities of an ideal impregnating medium? So they should be miscible or they should mix with the clearing agent. They should be liquid at higher temperature and they should be solid in room temperature. They should be homogeneous and stable. They should be non-toxic and cheap, transparent, and they should fit for sectioning the tissue. Now the time, duration and the number of changes which are required for the impregnation in the tissue, it depends on several factors. So what are those? The size of the tissue. Now thicker, larger tissue will take more time to impregnate with the embedding medium. It also contains more clearing agent to remove. So it will take more time for infiltration. Now the type of tissue. Again, hard tissue like the bone and cartilage will take more time for embedding than the soft tissue. The type of clearing agent. Certain clearing agents are easy to remove as compared to others, such as xylene and toluene are easy to remove as compared to cedar wood oil. Type of processing. Vacuum embedding enhances impregnation method. Now, paraffin wax. Now remember that paraffin wax, it is a type of hydrocarbon and it is a byproduct during the refining of crude petroleum. It is the most popular universally accepted embedding medium for tissue processing. This is non-toxic and inexpensive medium. The melting point of paraffin wax varies from 39 degrees Celsius to 70 degrees Celsius. The wax is sold according to its melting point. So paraffin wax with low melting point is soft in the room temperature, whereas paraffin wax with high melting point is much harder in consistency. So for example, if someone is working in United Kingdom, So over there the mean temperature is low, for example 29 to 30 degrees centigrade, like that. So in that situation, the paraffin with a lower melting point will be preferred. But for example, in the Indian subcontinent, where the temperatures are usually around 37, around 40 degrees, so basically a paraffin with a higher melting point of around 60 degrees centigrade is more suitable for laboratory use. Okay, total how much time is required? Total 3 to 4 hours of time in paraffin wax is sufficient for impregnation of the tissue by wax or infiltration of the tissue by wax. It is also compatible with most routine and special stains, including immunohistochemistry protocols. Okay, so paraffin wax, it is the most commonly used, inexpensive, non-toxic infiltrating agent, melting point being 39 to 70, and they are sold according to their melting point. With low melting point, they are soft in room temperature. With higher melting point, is harder in consistency. Therefore, it is necessary to have the paraffin wax that has suitable melting point to get a good ribbon of tissue. So in our climate, in the Indian subcontinent, the paraffin wax with a melting point of 60 degree is more suitable for laboratory use. So what are the advantages? As we have seen, they are non-toxic, they are cheap, safe, and the tissue block can be stored for a longer duration. What are the disadvantages? It may cause tissue shrinkage and hardening in case of prolonged impregnation, and paraffin wax takes longer duration for impregnation of tissues like the bone and the eye. So additives and modification of paraffin wax. To alter the physical characteristics of the paraffin wax, the following modifications may be done. To increase the hardness, we can add stearic acid. To reduce the melting point, phenanthrene can be added. For improving the adhesiveness with tissue and wax, 0.5% sericin can be added. Now DMSO, that is dimethyl sulfoxide, the addition of small amount of DMSO in paraffin wax reduces the infiltration time of wax and removes the residual clearing agent. It produces a homogeneous matrix and provides better support. Alternative infiltration media. So other than paraffin wax, what are the alternative infiltration media and what is the indication for using so? So what are the occasions where paraffin wax are unsuitable medium? So processing reagents. So for processing reagents, okay, remove or they destroy the tissue components which are subject of investigation, for example lipid. Now the use of heat may have an adverse effect on any tissue component, for example enzymes. In that case we should use alternate. So when we are using paraffin, we are using heat. Okay, so basically we cannot use paraffin if we want to preserve enzyme. Sections are required for thinner. Sections are required to be much thinner, for example for electron microscopy. The infiltrating medium is not sufficiently hard to support the tissue, for example undecalcified bone. So basically what are these agents? We are having resin. It is used exclusively as an embedding medium for electron microscopy, where ultra thin sectioning for high resolution, as well as for undecalcified bone we can use resin. Then we have agar. Agar gel alone does not provide sufficient support for sectioning tissues. Its main use is as a cohesive agent for small friable pieces of tissue after fixation, which is a process known as double embedding is done. When the fragments of tissue are embedded in melted agar, allowed to solidify and trimmed for routine processing. Other agents include gelatin and celluloid, and we will read in details about them in the next section as well. Okay, so do not worry about that. Now we are going to understand about the tissue processing methods. Okay, so tissue processing can be done either simply manually or with the use of automated processor. So in most of the government hospitals we are having both manual as well as the automated processing, but in most of the private labs now we are having the automated processor. So manual tissue processing is done only in very small laboratory with a handful number of tissue. Automated tissue processor is widely used in laboratories. Now the basic principle of automated tissue processor, it is to transfer the tissue in different fluid for a specified time in a desired environment. So there are two types of these tissue processor. The first type, the principle is, it is called as the tissue transfer processor. So as the name suggests, in this what is happening that the fluid is remaining the same, only the tissue is moved from one fluid to another fluid. Okay, so in this system the bucket of tissue is transferred from one carousel to another after a specified period of time. Now there are several containers with different reagents. The tissue remains in a basket full of cassettes. Okay, the basket containing the tissue is submerged in a specified container for a particular time and then transferred to the next container automatically. A gentle agitation is created by vertical oscillation or by rotatory movement of the tissue basket. The time schedule and the transfer of tissue in each container are determined by a microprocessor. So as you can appreciate, this is the tissue transfer automatic tissue processor. You can see that there are different fluids, different containers having different fluids, and there will be a basket containing tissue in different cassettes. So after a specified period of time, they will be transferred automatically to different containers like this, okay? And slowly, the tissue processing will occur. So here, the whole bucket containing the tissue is automatically transferred into the next fluid station. So over here, what is happening that after a specified period of time, it is the tissue that is getting transferred. That is why the term is called as tissue transfer processor. The second one is the fluid transfer processor. It is a completely closed processor. Here the tissue is kept in a container and the container is periodically filled with a particular fluid. So for example, this is a container and the tissue is kept over here. So for example, initially, some fluid is kept over here. For example, initially some fluid entered this container, remained there for 1 hour. Okay. Then after that, that fluid came out. Then another fluid we are adding. For example, we are adding, then another fluid is coming inside this particular container containing the tissue. Okay. Then again it is kept for a specified period of time and again it is taken out. Then again some other, then again some other is going inside. Okay. So what is happening over here in this particular method, you will see basically what you are going to notice over here, that basically that the tissue is remaining constant or the tissue is not moving, only the fluid inside is changing automatically. So after a certain period, the fluid is pumped out from the container containing the tissue. It is again filled with the fluid required for the next step. In this processor, each step can be customized for creating vacuum temperature and for a specified duration of time. So what are the advantages over here? The vacuum pressure makes the system faster and efficient, and in this closed system there is no chance for tissue drying at all. So as you can